Hi there. Today we're gonna make another example about the body plot, how to use them, and why they are so important. So last time we did a simple transfer function. This time it's gonna be slightly more complicated. Mostly because last time we had only a pool, so basically at the denominator, but we didn't have anything at the numerator, so no zero, just pools. But in this example, we're going to have both poles and zeros. So this time, our transfer function is going to be h of s. Whoops. Is my pen gonna? Yeah, there we go. Okay. So our h of s, our transfer function in this case is going to be s plus 1 over s squared plus 10s plus 100. Now, at the very bottom we have the 0 of the function, and at the very top, sorry, and at the very bottom we have the poles. So at the top we have the 0, and at the bottom we have the poles. Now, I know what you're thinking. We have a polynomial here at the denominator. So in order to, the first thing you want to try is to find the poles analytically. So, but if you do that, you're going to find out that we're going to end up with imaginary number. So if you say, okay, fair enough, this is s squared plus 10s plus 100, and I do okay, I'm gonna find the delta and so on. Well, let me just find s12 because of the delta. So it would be negative 10 plus minus square root of 100 minus 400 over 2. And here lies the problem. We have 100 subtracted to 400, so 100 minus 400, and then we're going to end up with a negative number under the square root, and that's actually going to give us a complex number. So the thing here is that it's actually, the roots we're going to find are complex conjugates. So it's not totally wise to take this, this path in order to solve the problem. So it's like it's actually easier to do something else. So first thing first, let's try to normalize, to go back to h of s, and let's try to normalize the denominator. So by normalizing it, I mean that I want to have something of s of 2 plus something of s plus 1 here. So essentially I don't want this 100 here. So I'm basically going to multiply, divide by 100. I can do that, it's not a big deal. So I will have 100 times s plus 1 over 100 times s squared over 100 plus 10 over 100 s plus 100 over 100, which will give me 1. So my h of s will be s plus 1 over 1 over 100 s squared plus 1 over 10s plus 1. Now that I've normalized this matrix here, I'm gonna do just like before. So I'm gonna set s equal to I omega. So my transfer function is now no longer h of s, but it's h of I omega. So I'm basically going to substitute s with I omega everywhere. So we'll have 1 plus I omega over 1 over 100 I omega squared plus 1 over 10 I omega plus 1. And again, this one in the numerator is going to be my 0, and this one, the denominator, is going to be my pole. So I can rewrite this as 1 plus I omega. At the bottom here, I'm going to say, okay, well, we'll just get I omega over 10 squared, and just bringing the square here, you know, outside the parentheses, plus I omega over 10 plus 1. Okay, what do we do now? Well, we're gonna bring everything into decibel, and then we're gonna analyze each and every one individually. So let's start with the numerator, so with the 0. In order to bring it to decibel, analyze it, we're gonna do 20 times log of the module, so the Euclidean type 2 norm of the 0, so of this one. So basically, this will give us 20 times log of the Euclidean norm 2 of this guy here, so 1 plus I omega, which is basically 20 times log of the square root of the first squared plus I omega squared, which is 20 times log of square root of 1 plus omega squared. So, whoops, I forgot to, yeah, there we go. Sorry about that. Okay, so 20 times log of the square root of 1 plus omega squared. Now, I'm gonna do just like in the former video. So I'm gonna say, okay, this is 20 times log of square root of 1 plus omega squared. Now, if omega is equal to 0, so it essentially, if this guy here is equal to 0, then it's just going to be 20 times log of the square root of 1. So this is 20 times log of the square root of 1. But we all know that the square root of 1 is 1, so it's 20 times log of 1. But 20 times log, well, basically log of 1 is 0, so it will be 20 times 0, therefore 0. Now, if omega is way greater than 1 though, so this is something extremely big, it's like infinity, squared, and we're going to add the 1, nothing is going to happen, and it's just going to be, and if we do take the square root, it's going to be 20 times log of omega. So essentially it is 20 times log of omega. Now, so far everything is being like pretty much like before, so nothing, you know, extremely surprising. So what do we do now? We plot it. We plot the pole. So here, this one, just changed my color to do a bit of color coding. So essentially, nothing is going to happen till we hit 1, which I'm going to try. Well, should have been closer to this, but that's not going to be in scale anyway. So till 1 is a 0. If you remember, you know, zeros go up, poles go down. So since it's a 0 and it goes up, at 1 it goes up. Therefore, we are expecting something like this to happen. Now, let's do the same for the pool. So for this big fat guy at the denominator. So 20 times log of the Euclidean type 2 norm, so the module of this guy here, this world guy here, it's not going to be something easy to compute, but there is a trick. So if I take and say, okay, I'm going to bring it to decibel, so 20 times log of the Euclidean type 2 norm of I omega over 10 squared plus I omega over 10 plus 1. Now, we could actually compute this and find the module of this, so the Euclidean type 2 norm, but that will waste a lot of time, especially if you are in the exam. You can't actually, afford to waste time like this. So what do? Well, we do exactly the same thing as before, right at the start. So we say that if omega is way smaller than 10, so something very, very little, then we're going to end up with negative 20 times log of 1, which would be negative 20 times 0, which is 0. It makes sense, right? Because if you take a look at this one, you can easily see that the dominant term is this square here, because it's squared. This is exactly why I didn't want to keep it this way, like 1 over 100 I omega squared, but I multiplied it and bring it I omega squared here at the top, and then I took the square outside the parentheses, because this way is extremely easy to visualize since we have the same basis. It's extremely easy to visualize that this guy here, which is a square one, is the dominant part. It's like when you take limits, except that this is asymptotical equality. So we can say the other thing. So if omega on the other hand is way bigger than 10, then for the very same reason as before, this whole thing is going to be reduced to negative 20 times log of this guy here, which is the dominant part. So I omega over 10 squared. So the module of this will be negative 40 times log of omega plus 40 times the log of 10. And we have this term here, which is a negative 40. So it's going to be a straight line, but the slope of this straight line is going to be bigger than the other one. So we had this guy here that was going up, but this guy, which was 0, because 0 go up. This guy here, which is essentially the pole, the pole goes down, but it goes down with a higher slope compared to the 0 because of this term here, which is a negative 40. So in our graph, now that I'm going to plot this, in our graph, we're gonna have the sensing graph. Whoa, it was I was going to, okay, just like this. So we said that 1 was like somewhere here. Now we're interested in this 10 here, and this 10 here is not gonna go, just like this, like the other one, but it's gonna go faster down than the other one because of this term here, which is negative 40. Okay, so essentially this guy goes faster down than the other one, which was going up with 1. Now, what do we do now? Well, I don't have anything else in my transfer function, since the transfer function was essentially just this 0 here and this pole here. So now I can use superposition basically and sum the contributions of those two. So if I sum the contribution of this one, which goes up, and the contribution of this one, which goes down, it does not go flat. It goes down because this one is stronger. It goes with a slope which is like this. So it goes farther down than this one, which goes up, you know, slightly less, you know, like as straight and as with the same slope as the other one. So if I sum them, I use superposition. I sum the contributions. I use superposition. Then what do we have? Well, we're gonna have a graph, which is gonna be our final graph for the gain. We haven't found the angle yet, but we're gonna do it very shortly. Now, this is 1, and I'm gonna imagine that this is 10, and should be I mean, the Bube should have made this one way longer. So this is 1, this is 10. So, oh, yeah, I didn't actually, yeah, imagine this to be here. Okay, so this is our graph. Up to 1, nothing happens. Okay, because, you know, this graph is flat, and this other graph is flat till 10. So till 1, nothing happens. I can easily draw it like this. Okay. Now at 1, from 1 to 10, this one is, you know, it keeps going flat. So its contribution is nothing. It's absolutely nothing. But this one, it starts to go up. So our graph is going to go up till it hits 10. Just like this. Now, at 10, we have 2 things, because, you know, this one is still going to go up till infinity, and it's really trying its best to go up. However, because of this term here, this negative 40 here, this one goes down faster than how this one tries to go up. So the winner would actually be this one. So essentially we would have a decay like this, which keeps going on forever and ever. Done. So this is it for the first part, but in the second part we haven't found the angle yet. So we got to find it. So the angle, which is you know, we use this notation for the angle. So the angle I omega will be just, well, if we actually remember, d0 here is 1 plus I omega. So essentially we will have 1 plus I omega. So we will have the tan to the negative 1, so the arc tangent, well, arc tangent of the imaginary part over the real part. So the imaginary part is I omega, so basically essentially omega, over the real part, which is just 1. So the arctangent of omega over 1. Now, since I have to compute the arctangent of omega over 1, I'm going to see 3 values. I'm going to see where this one, the omega, is equal to 0, when how it's going to behave where the breakpoint is, and how it's going to behave when omega is equal to 0. So let's do this. So for omega equal to 0, we would have the arc tangent. Shouldn't real. Why am I putting the G there? It's not correct for the notation. It's like lapses. Anyway, the arctangent of omega, which is 0 in this case, so 0 over 1, which is 0. So the arctangent of 0 is 0. Now for omega equal to the breakpoint, and the breakpoint in this case is 1, then the arctangent of omega over 1, when omega is 1, it will be 1 over 1. So it will be the arctangent of 1, which is 45 degrees. And lastly, for omega equal to infinity actually means the limit as omega approaches infinity of the whole thing. So of the arctangent of omega over 1. Now, what happens when this one goes to infinity? We will have something extremely big over something, very, very small. So it will be just the arctangent of infinity, essentially, which will be pi over 2 or 90 degrees. So our graph, our angle graph will be, try not to screw it up. Okay, so let me try to do it in scale. So around here we have 1, and around here we have 10. So essentially we'll be going up till here. So we'll be just like, we'll be going flat till 1 for the same reason before. It will go up till 10, and then it will be like this, the angle, and this midpoint here, this midpoint is what we found here with the breakpoint, which is 45 degrees. And this one here at the very top is what we found here as a maximum as it approaches infinity, so it's 90 degrees. So this is our angle, but it's not over yet, because this is the angle only for the this is the angle diagram in our Bode plot only for the 0, so the upper part, the numerator. Then we actually have to find the same thing for the denominator, so essentially for the pole. So let's do this. Ooh, I don't have space anymore, so I'm gonna use another paper here, but I'm gonna copy. I'm lazy, so I'm just gonna copy this one, not to to flip it several times. Okay, so our pool was actually this one, so let me just copy it here. So it was 1 over this one, I on omega 10. Okay, so let me copy and rearrange this as 1 plus I omega over 10 plus I omega over 10 squared. There we go. Okay, this one. Now, as I said before, oh, let me just, okay. Now, as I said before, these angle, this phase diagram is only for the numerator, so essentially for the 0. But now we're going to find the angle for in the phase diagram for the pole as well, so for the denominator. How do we do that? Well, first of all, let me just multiply this by its complex conjugate in order to get something, you know, more useful. So it will just be 1. Oh, this was, let me just, was it 1 plus? Okay, yeah, it was 1 plus. Okay, that's absolutely fine. So it was 1 omega squared over 100 plus I omega over 10 times 1 minus omega squared, running out of space, over 100 minus I omega over 10, everything over 1 minus omega squared over 100 minus I omega over 10, and this will actually give me one, well, the top part is going to be the same, so it will be 1 minus omega squared over 100 minus I omega over 10, everything over 1 minus omega squared over 100 squared plus omega squared over 10 over 100, I'm sorry. This will be negative omega over 10 over 1 minus omega squared over 100. And now I'm going to do the same. I'm going to try to see how it behaves for the 3 points, which are at omega equals 0, at the breakpoint, and at omega equal to infinity. Just like before. 0, then we're going to have a breakpoint, which is not going to be 1, it's going to be something else, and then infinity. So for omega equal to 0, we will have the arc tangent of these, but omega is 0, so negative, well, omega over 10 over 1 minus omega squared over 100. So will be 0 over 10, 1 minus 0 squared over 100 will just be essentially the arc tangent of 0, which is 0. Now, I have a problem though, because I'm actually facing a very, very, very big problem. I'm really tempted to say for omega equal to 10, but then something bad is going to happen. Because if I say for omega equal to 10, which is my breakpoint, something's going to break, but for real this time, and hit me really, really hard. Because it would essentially have the arc tangent of negative 10 over 10 over 1 minus 10 squared over 100. So would you say, okay, this one is 1, so it's fine, it's negative 1. Downstairs we have 1, and we will have 10 squared, which is 100, over 100. So 100, those two cancel out, we have 1 over 1, so it will be negative 1 over 1 minus 1, and here is the problem. 1 over 0. And this is the problem I'm facing, because at my break point something bad happens. So what I gotta do in this case is something a little bit particular, because okay, I'm gonna say, okay, fair enough, this is a singularity point. So I gotta study the function before and after 10. Now, for omega a little bit less than 10, the function behaves normally, because we would have the negative arctangent of omega over 10 over 1 plus omega squared over 100, which is essentially, if you recall, the graph of the arctangent is just this, with the two asymptotes here, on top of the bottom, pi over 2. So 9 degrees. This is the arctangent. Now, for omega greater than 10 though, the function is gonna jump and it's gonna reach pi. So essentially what we have would be the negative in front of everything of the arctangent of omega over 10 over 1 plus omega squared plus 100, and we're gonna add a pi at the very bottom, and well, at the very bottom and the very end. So since we are adding a pi, our graph, if we're gonna plot those two, will be, well, something that you may be familiar if you're familiar with Riemann surfaces as well. But so this one at the bottom is this one, okay, but then the function is gonna jump and we're gonna have something like this because of this pi jump, just like that. So therefore our final graph, our final plot for this whole messy thing for the angles of our body plot, so the phase, our final phase plot, is gonna look something like this. Here is our 0, here we're gonna have our 10, here we're gonna have our 100, and it's gonna go down till it reaches 2 times the 90 degree. 2 times 90 degree is negative 180 degree. So essentially we'll go down, like, let me try, can I get a straight line till there? I don't think so. My artistic skills are kind of bad. Yeah, but I somehow managed to. Yeah, this is, no, I didn't. I miserably failed. Well, let me just cheat and say that this one is negative 180 degree. Yeah, I miserably failed. And this midpoint here will be at 10. At 10 will be negative 90 degree. Okay, so this is the one. But it's not over, because, well, this is our final graph, but it's not the one made with the superposition of effects for the angles. This is the graph of the lower part of the poles, and up here we have the graph for the 0 of our transfer function. Now we gotta sum those two graphs together to get a new one, which is really our final graph. For real this time. So our final, phase graph in our Bode Plot example for this weirdly looking transfer function is going to look like this. Well, here we had that nothing happened till 1, then it was going to go up to 90 degree, and then it was going to go flat for the 0, so for the numerator. Down here it was going to go straight down till negative 180 degree till 100, and it was at minus 90 degree at 10. So what do you think is gonna happen? Well, we're gonna have that till 1 nothing happens. At till 10 nothing happened again, because at 1 nothing happens because it's always 0, but at 1 is going to go up to 90 degree, but this one is going down to 90 degree, and then at 100 is going to go down. So let me just plot it. So gonna go flat, 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 flat again, and then it's gonna go down, and then it's gonna go flat again. So this midpoint here will be negative 45 degree, and this point here is gonna be negative 90 degree. So yeah, that is pretty much it this time for our Bode plot.